Thanks. Stage is yours. Okay, very happy to be here. Yeah, I'm an virtual institute called Data Econometrics, Algorithms and Learning. It's a virtual institute. It's a joint collaboration of these universities in Chicago. I will talk about statistical and computational aspects in machine learning. Feel free to ask and interrupt and everything that comes up to your mind. There would be three parts from the talk. First, I will talk about research overview about broad question I've been working on. Then I chose a question that is more computational. It's about when we can change a training distribution, we can learn much faster. The other part would be more information theoretic, statistical, showing that in some sense, in overparameterized models, we cannot avoid privacy attacks. Okay, so let me start with some success of modern AI. Roughly in 2012, there was this AlexNet, a very successful network for learning vision tasks. 2016, people used reinforcement learning and research to come up with a machine that beat people in Go. 2018 till 2024, there is this AlphaFold. It's a machine that predicts how protein fold. People got a Nobel Award in chemistry for that. And DALI and ChatGPT you're familiar with. But let me also tell you about some failures. So people were able to show that these machines can reveal sensitive information about the training data. Autonomous cars crash sometimes, Waymo, Tesla, for various reasons. This is my favorite one. Taco Bell decided to use AI-assisted machines, and someone got 18,000 bottle of waters. So the general theme is about trying to understand theoretically what's going on. Hopefully, we can develop new language and try to come up with solutions. Okay, very broad overview about topics I've been working on. The general theme is about efficient and reliable machine learning. The most basic question is about resource efficiency, how much computation, how much information we need for learning. Learning in challenging environments. Let's say I want to use learning algorithms to learn in game theoretic settings. So people have been shown that you can use learning to compute equilibria. The most basic one is to compute min-max in zero-sum games. But you can use it also in more complex equilibria systems to learn correlated equilibria and so on. More about reliable machine learning, so robustness to noisy inputs. The most familiar one is adversarial examples with overparameterized models are sensitive to changing their inputs at test time. Privacy, mostly about models that reveal sensitive information about the training data. And in general, I have interest in the broader field of algorithms, especially beyond the worst case analysis. I've been working on some problems in learning augmented algorithms where you get an algorithm gets an advice from a machine learning model. Smooth analysis, how to analyze in between average case and worst case. And in general, I care about instance optimality, algorithms that adapt to the structure of the problem. If the instance is benign, then I can compute things fast. Otherwise, I want to recover the worst case. Okay, so I chose to talk about two different problems. The first one is about efficient learning, computational complexity, in terms of computational complexity through data selection. So we're gonna change the learning scheme slightly. The second one is about memorization in modern machine learning. Any question about one of these topics? Okay, so I call this project Is a Good Distribution All We Need? Is joined with Marco, Elisabetta, Tio, Gal, Nati with my daughter Nina in Sukkot, and Nina a few weeks ago, and also a new project with Nader Bashuti. Yeah, I don't know if you can see. Yeah, this is Nati with Nina. In one line, what this project is about, we want to show that even simple algorithms or algorithms that people use in practice, SGD on a neural network, can learn efficiently our problems, but we need to change the training distribution to see that. Okay, so this is in one line what we're going to do. So
there's in an architecture specific way.
So I will show that, yeah, feed-forward neural network, SGD, yeah, very simple. Thanks. So it falls under the paradigm called data-centric AI, where people focus on designing the data instead of finding new algorithms and architectures. So in particular, GPT, the architecture and the algorithm were pretty similar between the models. They just scaled the architectures. They had more parameters, and they added much more data, and they improved the quality of the data. Okay? So the improvement came from designing the data. Okay? Another nice example recently is that people showed that, okay, you have topics, you have examples from various topics, but if you choose smartly the mixture, then you can converge much faster. This one is 3 times faster. Okay, so basically the shift is about, let's focus on the data, fix an algorithm that we know that we can use in practice, but try to invest money and time in data selection. What it means, in the past, we were roughly in model-centric AI. You fix the data, then you try to find the best optimizer, the best algorithm. Data-centric AI, so-called, you fix the algorithm in the model and you try to optimize over the data. Some examples, classic examples are about data augmentation, synthetic data. Something more recent, I think is really interesting. Let's say you have a math question. The question is short, the answer is short. But if you give the algorithm in training time the reasoning traces, then the algorithm can learn much faster. It can internalize the chain of thought. Okay. Obviously, at this time, you don't have this chain of thought. So basically, you augment the training data with much more information about how to solve the question. Then it improves the learning process. Another one is about curriculum learning, where you give examples in order of difficulty. You first start with simple examples, and more complex. Yes.
Yes, listening, the learning and the difference is the same.
So I'm going to, okay, that's a good question. This is exactly what we're going to do. So in the classic learning scheme, the train and the test would be the same. We're going to change only the training distribution, and we'll show the good things happen. So yeah, I'm going to change the training distribution in 1 or 2 slides.
And you don't deal with these questions of there is a shift distribution.
So we're creating the shift on our
You are
own.
creating the shift.
Yeah, that's why it's going to be positive distribution shift, because we're going to create a shift to improve something as opposed to traditional distribution shift. And I have 2 slides of in a second. Thanks. Okay, so let's talk about the learning scheme. There is unknown data distribution. I sample from the training data. I have a learning algorithm that observes the data and outputs a model. Then I care about the test time on a random example from the same distribution. The statistical question is about how many examples do we need such that there exists a good hypothesis, small test error. The computational question is about how much time it takes me to find one. Okay. Many learning problems are statistically easy, meaning the sample complexity, how many samples you need, are polynomial in the problem parameters, but computationally hard. So we're going to focus on the computation here. And the goal would be to solve problems that are computationally hard in the previous model and show that we can solve them more efficiently by a simple algorithm, by a SGD on a neural net. Okay. So that's how we change the model. We design a new training distribution D prime. We sample from it. Then the algorithm observes S prime. But the test distribution is as is. It's the same D. So let me clarify what I'm changing. I'm changing the marginal distribution over x's, but y given x remains the same. So I'm not changing the labeling function. I'm just think about reweighting of the marginal distribution over x's. The test distribution is the same, labeling function is the same, and I'm fixing a learning algorithm that I know that people care about, such as SGD on a neural net. Take a look. I will talk about it for the next 10, 15 minutes. So this is a very general framework. I'm going to talk about specific aspect of it, but I think it captures many interesting things people are doing. Any complaints?
Yeah, it's just supervisor, right?
Supervisor, yeah. Let's put it into context. When you say distribution shift, people think about the negative aspect of it, meaning it's easy for me to train my model, I don't know, my autonomous car in one environment, let's say California, but I want to deploy it in New York. It's much harder to collect information in New York. Usually I would pay some cost between these 2 environments. There is weird hallucination here, I cannot see it, never mind. Okay, so this is to put it into context, we call it positive distribution shift because we're creating the shift to do better. Usually the shift is something we want to deal with. It's a problem. How people approached computational hardness in learning. One thing, they made an assumption on the marginal distribution, that it's Gaussian and uniform product. But it doesn't really solve the problem because there are hard distributions that we care about. Another way is to give the learning model more power, in particular to choose certain inputs, not just sample from the distribution, also choose certain access, called membership query. And then what happens is usually people are required to design new specialized algorithms. Ishai had a bunch of papers in the field, starting basically in this field. But the focus here is different, okay? The focus is to focus on a generic algorithm and not find a specialized algorithm for any problem. I want to show that I can solve by a specific algorithm many problems. I don't want to change the training algorithm. So the approach is to fix a standard algorithm, and then we're going to show that for any target distribution, there exists a nice training distribution that helps me learn faster. Good. Okay. The meta question is to understand which training distribution are informative. Informative with respect to the target function we believe we're learning. The target function has properties. So we want to design training distribution that helps me to learn the structure of the function. In particular, what we're going to take advantage of, we're going to think about Boolean functions. We're going to think about their Fourier expansion. And I would like to design training distribution that helps me to learn the Fourier coefficients of the function. You can take advantage of many things. That's what we're doing in this paper. We want the neural network to be able to learn the Fourier expansion of the neural network. The way I'm going to do it, I'm going to start by a simple example that shows that we can do that. It's the problem of learning parity with noise. It's computationally hard in the standard model with PDS. PDS is positive distribution shift. We're going to show that it's going to be learnable efficiently by SGD on a neural network. We're going to show experiments. We have also theory for that. Then we're going to extend. Okay, someone could say, okay, parity with noise, it's a nice anecdote, but it works for general function classes with certain properties, such as sparse functions, functions that depend only on k coordinates out of the t coordinates in the problem. Also, I think this is also a nice, interesting function class. Sparse function in the Fourier domain, meaning functions that when I write them in the Fourier domain, there are only a few non-zero Fourier coefficients. Something that you should pay attention to. The new distribution, training distribution, may depend on the target distribution and the structure of the class, meaning would depend on the class of sparse functions, but it would not depend on the exact target function I'm choosing from it. Because then it's easy to lie and learn many, many complicated things. Okay? Otherwise, I can encode in the new distribution exactly the function I want to learn. So this is a little bit of a cheating. Okay, so
also depending on the test distribution, you could do that, right?
yeah, it depends on the test. So I'm going to sample from the test distribution and also.
I don't understand. Learning parity with noise is NP-complete.
Correct.
So how can you?
I'm going to change the game. It's NP-complete because you sample the secret from the uniform distribution. The training distribution is going to be far from uniform. So I'm changing the game. So I'm not solving an NPR problem.
But after whatever you do, you get an algorithm for the problem, right?
So I will show you in a second.
So at least non-uniformly, you have a solution. It's like solving it with circuit, right? But we believe that you can't solve learning parity with.
I will show you in a second what does it mean to solve it, and then I think you're going to agree that I'm not solving what you think I'm solving. Okay, I'm changing the game slightly.
Okay.
In a second,
And I just want to quote, it's not NP-complete, but we believe it's.
we believe it's hard. Yeah. I'm going to talk about it in a second. Let's have this discussion after I show my result and see if we have any. Okay, so the overview of the results. Learning parity with noise. It's not hard to show that you have a tractable algorithm if you change the training distribution. This is not really our result. But the main focus is to show it that you can do it by SGD on a neural network, experimentally, theoretically. K-junta function depends only on K coordinate. we have a tractable algorithm that depends in t and 2 to the k. You cannot avoid t to the k because this is the sample complexity of the problem. Okay, if I'm not changing the training distribution, the runtime is d to the k. We're going to change the training distribution so that the runtime is going to be 2 to the k, matching the sample complexity.
What is this? T, what is
T is the dimension of the problem. The input is of size t, and k is how many equivalents we're doing. Okay, so we're going to show it also for variants of SGD. Sparse functions in the Fourier domain. We have an algorithm. This is already a new result that runs in polynomial time in D and the sparsity. It's known how to be solved with adaptive membership queries. Attias has a result about it. But the focus here is on non-adaptive membership queries. So we're solving the same problem without adaptivity. That's why it's a new result. And all of these problems are believed there is not known a polynomial time algorithm in the standard setting where the training distribution equals the test distribution.
You have poly in there. The first row.
It's going to be linear in the end.
So you're solving parity with noise. Fish algorithm. How does it?
In a second.
That is correct.
Let's talk about parities. Let's talk about parities, and you will agree I'm not cheating. Yeah, it sounds like a cheat, but it's not. You can learn parities with noise with membership queries, right? If you're going to ask the standard basis, you can recover the support really easily, right? If you're going to ask the standard basis, you can ask, I don't know, E1, you will understand if one is in the support, yes or no. You can do it for all of them. Then it's easy to recover the support, right? If you're going to define a uniform distribution over it, it's also easy to recover the support. But parity with noise, you assume that someone samples uniformly the support. This is in a nutshell why it could happen.
So that also explains why changing the distribution helps you.
With that. Otherwise, you won't be able to do that.
I didn't understand.
So, okay, I'm going to show it in a second, but if you're going to use queries of the standard basis, do you agree that it's easy to ask deep queries and understand what is the support?
Yeah, if you have some advantage, yes.
Do you agree that if you're going to have a uniform distribution over that, it's going to be also easy?
Right, yeah. But whatever you do after that, you have to solve a problem without any advice, right?
No. So no. Here we're going to, the advice comes through the training distribution.
So what is the final problem that you solve?
Let me show you, okay? Let me show you. Okay, let me clarify why parity with noise should be interesting, not only for theoreticians. Rosenblatt, once developing the perceptron algorithm, the linear classifier, people figured that you need to have more than linear functions, multilinear perceptron, which is just straightforward neural network. So it helped developing networks for expressivity. Then people like Hinton showed that, okay, you have these networks, you want to learn some algorithm, you're going to use backpropagation, and then they showed that you can learn with backpropagation, multi-layer perceptrons, and to learn XOR, because XOR is not linearly separable. Okay, so it was a case study for many standard problems, standard developments in the past. Another way to look at it, any Boolean function you can learn with two parts. There is the linear part, and there is the part that comprised from XOR functions. So the linear part, there is no interaction between the features. Each one of them just contributes independently. But the XOR is the other extreme. There is pure interaction. If you change one bit, the label changes completely. Okay. So I would say this is interesting also in terms of for practitioners, because whenever you have dependencies you can model by XOR. Okay, so XOR is just another word for very like strong dependencies, and it's not linearly separable. Okay. Now I'm going to tell you what I'm doing. Parity is, what is a parity? Is so instead of working over 0 and 1, I'm going to work over -1 and 1. There is an unknown subset S of indices. This is what I don't know. If it's over 0 and 1, you just look at this subset and compute the XOR of the bits of this subset. Over -1 and 1 is just the multiplication of this x's. Okay, so this is a parity function. The class is all such parities. There is 2D. functions. What is the problem of learning parities with noise? The marginal distribution is uniform. The label is the parity, but there is some noise. Probability 1 minus eta, I'm going to observe the real label. Probability eta, I'm going to observe the opposite. So the target distribution ds comprised from the marginal distribution, which is uniform, and the y is the noisy parity. And there is some constant LOA. So let's say even if I know that the marginal distribution is uniform, even if I know this constant, even if I know that the parity is of size k, it is widely believed that the problem should run in times k, where k is the size of the parity. What does it mean widely believed? There is a lower bound for a certain family of algorithms called statistical queries. And the best known algorithm runs slightly better than exponential time. Also, it's used as a cryptographic assumption. And statistically, it's easy because there are only k choose d, d choose k functions. So the log size of that is k log d. Okay, so this problem is hard. I agree. But now I'm going to change this distribution. Okay. People that are not familiar with that, take a look and see that you understand what the problem is.
So you're saying statistically easy, but you mean information theoretically?
Yes, information theoretic. If you don't care about computation, this is how many information. Okay, so this is what we're going to do. This is an experiment. We take a dense parity, so the size of the parity is of size 25. The dimension is 50. We take two layer neural network with parallel activations. The width is reasonable. We use online stochastic gradient descent, meaning we sample a new batch from the distribution and update. The target distribution is uniform. In this case, we're going to observe this red line that actually will converge after roughly v to the k times, v to the k iteration. Okay? But we're going to change the training distributions to observe this behavior. What are we going to do is we're going to sample a probability half from the uniform distribution. But the probability half, we're going to sample that is far away from the uniform distribution. We're going to have a bias distribution, product bias distribution, where each xi is going to be sampled to be +1 with high probability, 1 minus 1 over d, and -1 with probability 1 over d. Okay, so we're going to prefer vectors with bunch of +1s and a few negative ones. If you think about it over 0 and 1, it's just preferring standard basis. And then we're going to observe this convergence. Okay. So what happens is that the network can use this information in order to learn the function much faster. Does it make sense? Why?
Yes, because it's a different distribution. It's an easy distribution.
If I'm allowing you to sample only from the uniform distribution, you cannot avoid d to the k. Also without noise even. Neural network cannot learn parity without noise even, with time faster than d to the k, even though you can do Gaussian elimination.
What's the difference between d-bias and just sampling uniformly from standard basis?
In this case, it's going to work the same. Yeah.
So this is just so that it is a distribution that has independent coordinates?
Yeah. It's going to look, the reason we chose that is because it's going to look similar to other function classes, but what you're suggesting is going to work well. So I'm not claiming that this is interesting, that some algorithm can do that. What I'm claiming is that this is interesting that the neural network doesn't know that it needs to learn parity. It's going to learn the function through the training distribution.
You do need to assume something about the algorithm, right? If you use a crappy algorithm, it will not work.
For sure, yeah. So there is a very simple algorithm that just samples. I'm going to show it in a second. We cared about this specific algorithm.
Do you assume about it?
No, it's SGT on a neural network.
No, but in the analysis, we have to assume.
The theory, you mean?
Yeah.
Okay, good. So in the theory,
You can say about it, or
no. Let's talk about it. I'm not hiding anything. So this is like standard training. in the theory, what we do, we're doing layer-wise analysis. We freeze one layer, we train the first layer, then we freeze the first layer and train the second layer. It makes the problem convex. That's why we can analyze it. Another thing we're doing, just for simplicity, we add L1 regularization once we train the first layer. It helps you recover the support really easily. So in the theory, we are making some assumptions. The layer-wise assumption is everyone's making this assumption, but at least the theory validates everything we want.
But set the kind of analysis for a general algorithm, right?
So the analysis is for SG. Specifically, we cared about SGG and neural net. I'm going to show a simple algorithm. I'm going to show you in a second. Just sample with high probability to recover the support. It's not going to be very interesting.
You have the same sample twice, and for unit vectors, you're supposed to be getting a lot of these. Are you getting the consistent answers, or you're getting?
So the noise is IID.
Meaning that if you ask the same question 10 times, you would only get, by majority, you would get the right answer.
Correct, yeah. But this is already hard in the standard setting. So I try to find the simplest setting such that I can show improvement. But it's already hard in general.
Half the original distribution.
Could be a constant. Could be a constant. It doesn't really matter. It's going to just prove the constants. But I will tell you why I need that in general. Okay. So what is the intuition? Under the uniform distribution, there is some structure that I cannot observe unless I sample enough. What do I mean is that each individual coordinate and label, the correlation is going to be roughly 0 whenever this index is in the support or not. So I'm not going to observe this low order information. In particular, I'm not going to observe any information as long as I don't sample the parity completely, because all parities are orthogonal to each other. Okay, so to observe some signal, I need to sample exactly the parity. What the network is doing, it's quite interesting. It introduces coordinate label biases, correlations between the xi and y whenever I is in the support or not. Then the network can, in the first layer, recovers the support, which is the hard part. And then in the second layer, once you know the support, there are many functions you can learn. There is no reason to learn the function of parity. You can learn much simpler functions. So you still need to sample from the uniform distribution to know which function you need to towards. Okay, so there are like two phases. The first phase, the network recovers the support, and the second layer, the network figures out which function to compute over this support.
That if you know its parity, once you know the support, you know the function.
I agree. That's why the network is interesting, because the network doesn't know that you need to learn parity. So what you're claiming is this algorithm. Let's say I know I want to learn parity. Under the bias distribution, there are going to be these correlations. The expectation between xi and y is going to be larger whenever I is in S or not. And then it's easy. You can sample enough, 1 over that terms squared. With high probability, you will understand if I is in support or not. Then you can do it for any index, and then you can figure out what is the support. But this is when you know that you're looking for parity. The network, I'm claiming that the interesting claim is that the network does that through the distribution, the training distribution. Does it answer the question?
So the only hint the network gets is you should consider unit vectors more.
Yeah, yeah. So this is not very fascinating, but the fact that you can do it for a network, I think it's not true.
So this would work even if I work with uniform distribution over standard basis vectors.
Yeah.
So that would mean some kind, you can think of it as some kind of implicit bias, but because it can fit these unit vectors into.
Yeah, I heard this comment. How do you see it as an implicit bias of what? That's
Basically, it's the way I think about it. Is that you can fit the training data in various ways. Some of them generalize, some don't, and what SGE finds is one that generalizes.
yeah.
But you have to depend. Do you have to have those sampling from the uniform distribution? Can't be zero, right?
So in some classes, you don't need, you mean the probability I have to sample from the, yeah.
Left average? Because let me maybe phrase it as a question. If it's not the case, and there's only one way to fit the data, like only one function that actually fits the data, and this is purely a computational question.
So, okay, you say, let's say I try to feed the unit vectors, then maybe I recover the support. But then you need to have some signal to understand which function you want over this support.
No, I'm referring to the statement that the network doesn't know that it's a parity function. What I'm saying is that if there's only one solution that fits the training data, then this kind of statement would be less, that it does know, right? Because the training data.
So what you mean is that we don't give the network any option, but to figure out this is the fair.
Either that, or there's some kind, I can think about it as implicit bias.
Interesting way, yeah. I don't know, I haven't thought about it that way. Yeah, it's incredible.
But I think you're operating in the regime of parameters when there is a uniform convergence sense, right? Every solution will be good, right? There is no statistical difficulty here, right? As you were saying before.
Uniform convergence.
Every solution that you will find using your algorithm will work.
I'll tell you what happens in these functions. We recover the function exactly. Okay.
Oh, I see. This is
what happens. In parity and other functions, once you recover the function completely, it doesn't matter what is the distribution. But for DNFs, it's not going to be the case. So for DNFs, it's going to be different because you can only do it for the target when the target function is uniform. Okay, so I think the answer is that for some function classes, you recover exactly the function, meaning it doesn't matter what is the test distribution. You just find the distribution and helps you recover the function. In some other cases, it's more complicated. Okay, let me summarize. So we can show that for any distribution D, there exists some D prime that I can sample from, such that if I'm going to train with SGD on a neural network, I'm going to learn this class efficiently. Formally, we're making the assumptions as Tomer asked. Experimentally, we are not cheating at all. It's very standard SGD, two-layer neural net.
I don't understand. So this has nothing to do with learning, right? I mean, if you just, you just change the problem and now it's easy. So
I mean, learning algorithm.
I mean, this is very different than saying that you can solve parity.
I'm not solving parities. I'm changing the game so that the network would learn parity with
Yeah, but now if you go to the real world and you want to solve parity with noise, you have no clue how to do it.
I agree, but the claim is that statistics people would call it experimental design. Meaning, I'm going to sit in my lab, come up with some experiment. You're going to say, okay, if you're going to sample that way in the field and come back with the solutions, I will be able to recover something about the signal. Think about compressed sensing, for example. I need to do something. Yeah, I'm not going to solve parity with noise, right?
Okay. I'm not saying you're doing nothing. I'm only saying, but you didn't solve parity with noise. This is.
I agree 100%.
Yeah.
Because it's a hard problem. I cannot solve parity with noise.
Convince the lower bounds, right?
Okay.
That's the case.
We agree. There is no, yeah, I agree. Okay, so let me show you that I can learn also more interesting functions. So let's say now f is not parity. It's a junta. It's a function that depends only on k coordinates. Okay. I think this is an even more interesting experiment. So the dimension is 50. The number of relevant parameters is 9. I'm fixing the target error to be 0.01. Again, the target distribution is T. The training distribution is going to have the same form. With probability half, I'm going to sample from the uniform distribution. But with probability half, I'm going to introduce biases to all directions symmetrically. So in the parity, I gave a bias towards +1s. Now I'm going to, with probability half plus some epsilon I, which is uniform, I'm going to sample to be +1, and probability half minus epsilon I, I'm going to sample to be -1, and this is symmetric. Okay, so this is a different type of biases. A way to write it is I sample uniform distribution. I sample from the uniform distribution U, and then ui plus, I'm sampling ui plus 1 over 2 to be plus 1, and otherwise negative 1.
Are you shifting the difficulty to finding the
Yes.
the bias distribution?
So
You said that there is the distribution, and
Correct.
then you come up with the distribution by magic for specific problems, or
correct. So the general claim would say that for any D and H in function class, there exists D prime and an efficient algorithm.
yeah,
But here I'm showing
you
you.
can find the prime.
But here I'm showing you how to find D prime.
But for a specific class of problems for which neural networks might not be a particularly good algorithm.
I partially agree, because for interesting function classes, first I'm just telling you that there exists D prime. Then for interesting function classes, I show you how to find them. And I give you also a recipe. The recipe would be to increase the signal in the Fourier spectrum. The reason this works is that if a coordinate is relevant, then in the shifted distribution, the Fourier coefficient corresponding to this index is going to be large. So that's what I'm doing here. As long as I can detect or learn the Fourier coefficients, that would be the recipe. That's how I'm doing it for this function. So there is some general recipe. Okay, so this is the experiment. You can see similar behavior. This is another experiment that you can show how many samples you need, which is the same as the number of iterations as a function of the input dimension. The theory would say that we improve from D to the K to 2 to the K. And you cannot avoid 2 to the K because there are going to be at most 2 to the K Fourier coefficients, and the sample complexity is 2 to the K. So you cannot improve that. So what happened is that I'm matching the computational complexity with statistical complexity by changing the training distribution. Okay. Let's shoot one slightly faster. Okay, general message. The takeaway from this project is that we should learn the dynamics of the training dynamics as a function of the training distribution. We can speed up the learning process. In general, it's interesting to give a general recipe which distributions are good distribution for learning some specific function as a property of the target function. But there's no free lunch, as you said. I need to assume something about the target function. I believe that the target function has some structure so that I will find D prime. I'm shifting the difficulty somewhere else. In some sense, it's interesting to apply to practical tasks, but the bigger picture, I think, is that this is only one framework for learning data selection in a formal way. I think there is room to develop language for why that data selection is working and why people are doing it in practice and why. Let me have 10 minutes, right?
Thinking a little bit more, but
I will.
12:10.
Okay, 12:10 is enough.
Room explodes. Okay,
Cool. So this is about memorization and privacy attacks in learning. This is with Carolina, Madi, means Mashiach. Everybody. And this is recorded. Roy Livni, Dan Roy, and Sasha in Farsi. Yeah. Based on 2 papers. So what was the motivation for this problem? People observed the following behavior. You increase the network size. Then, okay, the training error goes to 0. This is not surprising. You have more degrees of freedom. But also the test distribution goes to 0. So how this is possible? It contradicts what we would believe. But what happens is that we choose a simple algorithm like gradient descent, and it prefers simple solutions for the implicit bias. But effectively, what happens is that you get 0 training error, meaning you learn the noise and you learn outliers in the problem. It's not a new phenomenon, because roughly 30 years ago, people observed the same things with ensemble methods, with random forest, tagging, and boosting, where the complexity of the function corresponds to how many classifiers you have. The test error goes to 0 and the training error goes to 0. Okay, so the motivation is that you learn some noise and outlier in the data, meaning there is some privacy risk. So we're going to talk about a privacy risk I'm calling membership inference attack, which means the following. Let's say I'm giving some attacker a pool of examples from the distribution. Some of them participated in the training data and some of them are not. And the attacker should say which is which. If the attacker detects samples in the training data, it's some privacy violation because someone would know that I participated in the experiment. Other types of privacy risks is reconstruction of the training data. But here they are assuming that they know what is the learning algorithm. There is also extraction from the diffusion models. But the general question we cared about is, okay, these things happen, but maybe there exists some good algorithm that avoids that. Maybe we're not doing something right. And it's possible that we're going to have a good learning algorithm and we're not going to have a privacy risk. The answer would be that this is not possible. In some cases, it doesn't matter what is your learning algorithm. Good function comes with large correlation with the training data, which translates to information attack. Okay, so the solution that fits is that people observe that, and there is a good reason because you cannot avoid that. Okay. So we're going to focus on membership inference attack. There are many applied papers about that, and we're going to give a justification, a theoretical justification. Okay. What's the message? We're going to take a simple learning model, stochastic convex optimization, but you can just think about linear regression. Many of the results called for linear regression. And the claim is that any good learning algorithm, meaning with small test error, where the number of parameters is not larger from the number of samples, implies that there is an attacker that can detect a fraction of the training data, can do membership inference attack of 10% of the data, meaning you cannot avoid this privacy leakage. And overparameterization is necessary, since if the number of parameters are smaller than the number of training samples, you have differentially private algorithms. But on the other regime, is not that you don't have differentially private algorithms, you lose much more. You lose a fraction of the training data. Okay, so there is a phase transition from differentially private algorithms to losing a fraction of the training data. You cannot protect a few people, not just one individual.
So this only also certain class of algorithm, right?
This is for any algorithm.
But then if I have a learning algorithm that uses few parameters, I can pretend that they have tons of parameters.
Good question. I'm going to force it through the training distribution. So I'm claiming that for some training distribution, this is going to happen. It's not going to happen for any.
Depends on how I update my parameters, right?
True, but if the distribution requires that you're going to have many parameters to have small test error, I'm going to force you to use all the parameters through the distribution.
You tend to only care about algorithms that cannot be learned with few parameters.
Correct.
It will apply to good algorithms, right? Algorithms that can learn.
Yeah, okay. Okay, so I have maybe a better solution. You're not going to be able to reach epsilon test error if you're going to lose fewer parameters. So I assume the algorithm is good. For some distribution to be good, you need to be overparameterized. I think this is the answer.
So this is an example for specific distribution, not any learning problem.
Sometimes, yeah, will be more careful. Like, there are some distributions where this is not the case. You can use fewer parameters. Once I force you to use many parameters, this is the case. This is it's a worst case analysis. Okay, so to summarize that, sometimes I will be able to avoid that. For some distributions, we show scenarios where you cannot avoid. Okay, so what is the model? Look at the same scheme, learning scheme. Now the model comes from a class of parameters. Let's say parameters in a unit ball. Let's say take the diameter to be 1. Think about linear regression, okay? The loss function is convex and Lipschitz in the parameters. Again, think about linear regression. It generalizes some classic learning model, logistic regression, training with hinge law, support vector machine, linear regression, and so on. Okay, put in your mind linear regression, and the number of parameters is larger than the number of samples. Why this is an interesting setup? Because the sample complexity, how many samples I need to learn, is independent of the dimension P. Depends on the Lipschitzness and the diameter of the problem parameters. And also another aspect is that I can learn with specific algorithms such as SGD, but if I'm just gonna minimize the training data, I won't be able to learn. Okay, so there are two aspects. The sample complexity is independent of the dimension, and certain algorithms succeed better than others. It has some key properties of modern machine learning, and we're gonna show a negative result. Okay, so we take a very simple model to show a negative result. We're happy about that. The simplicity is an advantage, it's not a disadvantage. What is a membership inference attack defined by many people before us? Very simple. There is an attacker, is given some targeted individual, X and Y, and let's say it has access to the model parameters. We can relax that. If this individual is a member of the training data, the attacker should say yes, otherwise the attacker should say no. And the goal is to identify as many individuals in the training data as possible. So this is an attack on one person. What it means the attacker to succeed in many examples. So a model is K alpha traceable if there is some attacker, such that the attacker could identify K individuals in the training data. It would say in on at least K individuals, maybe with constant probability. But okay, the attacker could say always yes. So we need to have another criteria. The criteria would be that with small probability, the attacker would say yes on a no instance. Okay, so the attacker identifies at least K individuals, and with small probability would say yes on a no instance. What is the theorem? Any overparameterized model with small test error admits settings. This is what I mean by there exists distribution such that there will be an attacker that's going to detect a fraction of the training data, meaning if I use 1 over epsilon squared samples, the attacker would be able to detect 0.1 times 1 over epsilon. Any questions about message? Okay. Let me just highlight what is the mathematical idea, the main mathematical idea behind the result. It's a very simple claim that says that if I have a good estimator in high dimensions, it comes with the cost of large correlation with the training data. So this is called fingerprinting lemma. It came from cryptography where people use fingerprinting codes. And the lemma says the following. Let's say I have some fixed mu, okay? Then I sample from a distribution with expectation of mu. Then if I have small mean squared error, it means that I'm going to have large correlation. This is basically when you fix mu, this is the covariance. You're going to have large correlation because this is bounded from below by a constant. If you're gonna sample mu, it means that there exists some mu, there exists some distribution, such that if this is small, there is large correlation. When there is large correlation, you can translate it to privacy attack. I think it's an interesting fact to know. This is the very simplistic form of the lemma. It has many variations. This is one-dimensional, so you can generalize it for a product distribution. Okay. So the main idea behind that is a fingerprinting lemma. What it means to privacy. Okay, what is privacy in one sentence? The output of a model is going to be similar whether I'm going to participate in a database or not. Okay? Meaning the algorithm does not depend on my entity in the database. And what we see is a phase transition. If the number of parameters are smaller than the number of training samples squared, then it's known that we have private algorithms. On the other regime, it was known before us that there are no private algorithms, but we show something stronger, meaning no private algorithms, meaning I cannot protect one individual. This result showed that we cannot protect a fraction of individuals. Okay, so at least in this model, I don't say it's any model, in this model, there is this phase transition as a function of the number of parameters, and I need distribution that actually requires so many parameters. Okay. What is the takeaway? In high-dimensional settings, sometimes there are going to be scenarios where you won't be able to avoid this privacy leakage. There are many other interesting ways to measure memorization. An interesting definition would be reconstruction of the training data. There is not one acceptable definition. Uri and Ishai they wrote a few papers recently about what it means theoretically to reconstruct training data. I think already here the question is interesting, like just define what it means. Reconstruction we cannot live with. And the big picture, I think, of this type of topic is understand what is a vulnerability. If we care about privacy, what is a vulnerability of large models? Then once we understand the vulnerability, we can think about what we want to do in order to solve. Okay, so let me summarize. So I showed you two types of projects. One of them was computational, one was more information theoretic. The goal was to understand something simple that happens in real tasks. In the first project, we gave new language, new methodology to understand why people are doing data selection. It's only one way. There could be many other ways to formalize it. In the second project, actually, we gave a theory justification to what people observe in practice. It falls under the larger topic of efficient and reliable machine learning and sequential decision-making. One topic I care about is adaptive algorithms, and algorithms that exploit structure in the data if it exists, meaning if the data is generated by simple mechanisms, we can learn fast, but if not, we can still recover the worst case, instance optimality in learning. In general, resource efficiency in learning, how much human feedback we need, computation, memory, and so on. And reliability is about privacy, robustness, and also using learning algorithms in multi-agent systems, game theoretic settings. That's it. Questions?